The 175 billion parameter GPT-3 model has wowed the public with its ability to generate text autoregressively by predicting masked out tokens. Another capability of GPT-3 that excited the AI community was its few-shot performance. Few-shot learning describes a setting where we have a very small set of labeled examples. GPT-3 generally relies on 32 of these labeled examples and a description of the task. This learning paradigm is extremely interesting because curating these massive datasets is tedious, and it would be really interesting if these models were able to perform tasks with a very small labeled dataset. The authors of this paper show that you don't need an 175 billion parameter model to do few-shot learning in natural language processing. They adapt the pattern exploiting training algorithm, which unifies the generative language models with discriminative classifiers through the use of patterns and verbalizers. This video will explain how PET works, the Iterative PET variant, the use of semi-supervised knowledge distillation, the proposed PET with multiple masks, and many more. This video will explain the paper. It's not just size that matters. Small language models are also few-shot learners. This paper was recently trending on Hacker News with the bold headline, AI training method exceeds GPT-3 performance with fewer parameters. And this is a big headline because the GPT-3 model is a very expensive 175 billion parameter model. So this idea that some technique has come out that achieves the same performance with less parameters is obviously very interesting. But this isn't really a fair comparison because, as mentioned in the discussion thread under this Hacker News post, the GPT-3 model does this few-shot learning as a byproduct of the language modeling. It wasn't designed to do this, and they're just kind of showing that it does this as a byproduct. Whereas this pattern exploiting training paper is going directly at that few-shot performance where you perform supervised learning tasks given a very small labeled data set. So it's not really a fair comparison to say that this exceeds GPT-3 performance because it doesn't compare with GPT-3 on the actual task it was designed for, which is language modeling. The thesis of pattern exploiting training and what GPT-3 is hinting at with its in-context learning is that all natural language processing tasks can be formulated as language modeling or closed tasks. So this is an example of natural language inference. The natural language processing task is to take as input x1 and x2 and then classify whether x2 is an entailment of x1. So this is showing how you can restructure this problem such that you integrate the mask token and turn the natural language inference problem into language modeling, predicting the masked out token, and then mapping the mask prediction to the class label. So pattern exploiting training comes with all these clever patterns and verbalizers to do this mapping of any natural language processing supervised learning task into language modeling. And GPT-3 does this as well with the context window having examples of the task and then giving a new example and then having the GPT-3 model do the mask prediction to perform the new task. Here's a quick recap of the pattern exploiting training algorithm. I made a full video walking through this paper if you're interested in that as well. So the pattern exploiting training idea is a way to leverage pre-trained language models for downstream supervised learning tasks. So the idea is distilling the knowledge learned from these generative language models into discriminative tasks like Yelp review classification or natural language inference. So the idea is we take the data that we have and we insert these patterns. So the original data might be something like best pizza ever, or we'd imagine a much longer Yelp review having been written, and we'll append this pattern. It was mask. So then the language model is going to fill out the mask, and then we're going to have a verbalizer that maps from the language model's outputs into the class label, and then we're going to use that for supervised fine-tuning on the small labeled data set that we have to update our language model to get better at labeling this data for the supervised learning task. And then we're also going to use this semi-supervised knowledge distillation where we're going to use the language model after it's been fine-tuned like this on the small labeled data set to start labeling a massive set of unlabeled data in this same kind of way using the pattern and the verbalizers. So another part of the pattern exploiting training algorithm is that we're going to construct several of these patterns, and we're going to use an ensemble of these patterns to help sift out the noise with respect to each of these patterns appended to the given task. Here's a quick description of how these patterns are filled out with these pre-trained language models. This is the next word prediction demo app created by Renato Violin and open sourced in a GitHub repository that's linked in the description of this video. So I've taken this example from the Hugging Face NLP viewer, looking at the bool q dataset. So here we have the passage. So this left half of this prompt is the passage that's going to be inputted, and then it's going to have to answer a question about the passage. So this is a passage about the Now You See Me movie, and then the pattern is based on the following passage, comma, and then the question that was part of the supervised learning. This is the question, this is the passage, and then it has a label as in yes or no, and then you have the mask. So based on this context, using the pattern based on the following passage, is there a Now You See Me 3 coming out? And then the language model is going to predict what comes next. So you see things like no, yes, yes. You see that this is kind of a disappointing performance. So that's why they use multiple masks. They fine-tune the patterns with a little bit of training. It doesn't really look like, based on the little bit of patterns that I played around with in this demo app, it doesn't look like this really works right off the shelf. So as you'll learn from playing around with this, the patterns need to be fine-tuned. So the strategy with this is the Iterative PET algorithm. So what they have here is they have an ensemble of different language models that are trained with different patterns, and they are used to label an auxiliary dataset that fine-tunes another, the one that's left out of the ensemble for constructing the new labeled datasets. So they distill the knowledge from the ensemble into each of these datasets and use it to update each of these patterns such that they converge to a more desirable behavior. And this works for distilling the knowledge in the pre-trained language model, and also kind of reining in the variance of these patterns and how you map from the output of a language model into the labels for the downstream supervised learning task. Semi-supervised knowledge distillation is becoming a really important piece of the representation learning pipeline with respect to these self-supervised learning tasks and distilling from these generative models into discriminative models. So this is also used in the SimCLR v2 revision of the original SimCLR algorithm, where they first learned representation with the unlabeled data doing self-supervised learning, the contrastive learning objective. Then they fine-tune that model with the small supervised learning data set, and then they do this distillation loop with the unlabeled data. So the idea here, and it's also used in Noisy Student, which has the current record for ImageNet, is you use the model to predict, you train a model, and then you use it to predict labels on the unlabeled data. And then you use the knowledge distillation algorithm of having this kind of soft target label distribution that comes from another neural network to train a smaller or a larger neural network in this kind of iterative distillation process. So what happens in PET is they start off by doing the supervised learning of the language model, mapping its outputs into supervised learning class labels, and then they do this for about 32 labeled examples to make it a fair comparison with GPT-3, and then they're going to label this unlabeled data and distill it into a smaller model or another model, or the ensemble of models as in the iterative PET algorithm, in that kind of loop to leverage this unlabeled data for representation learning. So before we look at some of the data sets that are tested in these experiments to understand how these different tasks are formulated as language modeling or closed questions, let's look at this trend. So previously in the T5 paper, and I think there was a paper that came before this as well, it was pretty surprising to see this text input text output representation, showing that you didn't need to have these classification models explicitly. You could have text input and text output, and it was a way of unifying all of these natural language tasks. So say in the glue benchmark, you have text classification, you have semantic similarity, entailment. You can unify all the different tasks to train one model that does all the tasks by having this text input, text output unifying framework. So it's interesting to see this kind of extension to all tasks or language modeling. So we're seeing this first trend in going to text input, text output, and now this trend is saying that we might be able to just set up all these tasks as language modeling tasks. So here's a quick tour of the different data sets that are explored in this paper. Small language models are also few-shot learners. So hopefully from going through the description of these tasks, you can get a sense of how they might be set up as language modeling tasks. So the Boolean question data set is a question answering task where each example has a passage and there's a question and you expect a yes/no answer. So we would have our mask, and hopefully our language model goes right to predicting yes or no and not things like maybe or definitely. You can see how this is the importance of having the verbalizers with respect to pattern exploiting training, because the language model has this output size of 30,000 tokens, say, something like that. So it's unlikely to just predict yes or no all the time. So you need to have a more sophisticated mapping to get to this Boolean questions supervised learning class labels. But you see how you have these questions, passage, question is the question, colon is the pattern, based on the previous passage is the pattern, based on the following passage is the pattern that you use to turn this task into a language modeling task. So they also test this out on textual entailment tasks like natural language inference. So this is examples from the ESNLI dataset, not the CB and RTE datasets that are used in the paper. But what you have is you have this premise and then you have this hypothesis, and you have to predict whether the hypothesis is an entailment of the premise. So the pattern is predicting yes, no, and maybe, and those outputs from the language model are mapped to entailment, disagreement, and neutral. So again, you have these patterns where the hypothesis is placed here, question mark, bar, mask, and then the premise. So another data set is this COPPA task, and this is the multilingual COPPA task that is all that I was able to find on the Hugging Face NLP viewer datasets. What you have here is you have these two choices. So you're determining which of these choices are the cause or effect of the premise. So you have the premise, and then you have cause 1 or cause 2, and then you label which of the causes. So you see here how the patterns have to start to be a little more flexible to account for a more dynamic task like this compared to, say, the text classification where we had good or bad with the pizza review. So here we're seeing further cases where it's more challenging to design the pattern that will adapt this task into a language modeling task. So in this WIC dataset, we're given a word and two sentences, S1 and S2, and we have to decide if W is used in the same sense in both sentences. So one example of this might be when you're looking through these medical data sets and you have PDF might refer to a gene or PDF might refer to a file format, something like this, some task like this, where you have a word, this disambiguation, or where you're trying to see if the word is used in the same in both the sentences. So the thing that we're interested in is how did the patterns adapt to this task? So we see S1, S2, does W have the same meaning in both sentences? That's probably the most on the head way of doing this. Then we have these other patterns like similar sense of W in these two passages. So you imagine inserting the S1, inserting S2, then inserting the word W. The Winograd schema dataset is the task of classifying which noun N a pronoun P refers to in a sentence S. So in this case, we see these different patterns of having the sentence S, then the pattern, the pronoun, quote, star, the pronoun P, star, quote, refers to mask. And then the mask would be mapped into this noun N. So again, we're seeing this case similar to the WIC task, where it's more challenging than, say, the Yelp review sentiment classification, where we can just say it was mask to describe the experience at the restaurant or whatever. We're seeing these cases where it's a little more challenging to set up the pattern that maps all of these different natural language processing tasks that are used to benchmark these systems into mass language modeling or language modeling tasks. So this is the multi-RC dataset. It's really similar to the Boolean questions dataset that we started off looking at, where you have the passage question and then you're just doing yes or no answers. So in this case, you have an explicit answer candidate A that you're using the yes or no prediction with. And then finally, we have this record data set. It's already set up as a closed question, so it doesn't require too much extra processing by the authors of this paper. So these are the different data sets that are explored in this paper, and then I recommend checking out any of them individually. A lot of them are on this Hugging Face Datasets NLP viewer, and then you can also just go to the links in the paper. The next slide will show the results comparing the pattern exploiting training and the iterative pattern exploiting training with GPT-3's in-context learning. So here's a quick recap of what GPT-3 is doing and how this approach is different to what we've just described. So GPT-3 does something called priming or in-context learning, where it has a description of the task, examples of the task, and then it'll have the prompt to do the new task. So say this new task is cheese and then translating cheese into French. So it starts off with the task description and then examples of translations from English to French. And this is all put as input in the transformer's attention input context window. So these transformers, they attend over this input sequence that might be, say, I think it's something like 2048 tokens in the GPT-3 language model. So you can have a pretty long task description to prime the GPT-3 model to be able to perform this downstream task. And this really is profoundly different from what PET is doing, because GPT-3, as discussed in that Hacker News thread, seems to be able to adapt itself to perform this new task. There's no gradient updates, and that's pretty remarkable. And PET doesn't work this way. Even though PET, as mentioned, these major drawbacks, is much more realistic. You know, the GPT-3 model is 175 billion parameters. It's not realistic for most people to use that kind of model, whereas this algorithm is much more realistic if you're trying to just do this few-shot learning capability, if that's the downstream performance that you're most interested in. This is the comparison of the different variants of the GPT-3 model, which is this decoder-only transformer architecture just scaled up with respect to the number of layers and sometimes also increasing the hidden dimension of the embedding vectors as well as the embedding vector sizes in the intermediate layers of the transformer, going up from 125 million parameters up to 175 billion parameters. So looking on the far right with the average accuracy, you see this phase shift in performance as you scale up the size of GPT-3, the largest model performing an average of 73% accuracy compared to 50% accuracy with 125 million parameters. And then this is the individual performance across each of the data sets that we just looked at, like Boolean questions, the entailment task, or the pronoun resolution task. So this is performance of PET and Iterative PET at a much smaller 223 million parameters. But again, this isn't really a fair comparison because PET is using this supervised learning gradient updates. It's also using this semi-supervised knowledge distillation with an unlabeled data set. So GPT-3 only sees 32 examples in the context window, and then it doesn't use any of the rest of the data, whereas the PET is still going to use this semi-supervised distillation with the unlabeled data. But if you're interested in doing this kind of few-shot learning and you have a data set like this, then PET is much more realistic for practical use than GPT-3 would be. The authors note that they're not able to get access to GPT-3 to test the results of this with the GPT-3 model, but look at the variance in the different labeled examples given to the PET model. So this different sum 0, sum 1, sum 2 is the different subsets of the 32 labeled examples for each of these tasks. So this has a huge variance of about 5.4% on the CB dataset when you have a different subset of the 32 labeled examples used to start off the supervised learning process. So I think it's a pretty interesting result seeing the variance in which of these labeled examples you use to do that small set of supervised fine-tuning. This table shows that the PET algorithm is actually able to perform pretty well without the semi-supervised knowledge distillation loop, but I wasn't really able to completely understand how they implement this, so I'm leaving the interpretation of this to you to look at the paper yourself. Another interesting direction the authors explore is the PET algorithm with multiple mass. So imagine we have this entailment task where we have oil prices rise, oil prices fall back, and then we have the mass that we're using to say entailment, neutral, not entailment between these two sentences. So you might also integrate patterns like more mass news, more bad news, good news that could provide more signal to predicting this label, and then I'm mass going to buy oil, also using more of this signal to tell the supervised learning label for this natural language inference task. So they have this more complicated details of how they do the inference and training for PET with multiple mass, mostly this idea of whether you want to do a left to right decoding of the mass or whether you want to predict each of the mass in parallel, and that kind of way, and how you actually integrate that and then put gradients back through that with respect to training and updating the PET model with multiple mass. But shown in this table, it doesn't look like they've quite figured out how to make this work yet. And it's also, they had a similar kind of end of the paper idea in the original PET paper with the automatic verbalizer search. So automatic verbalizer search, automatically trying to find how you map from the target vocabulary of the language model into the supervised learning class labels, as well as this PET with multiple mass idea, are two really cool ideas that will probably extend the scope of this algorithm. Pattern exploiting training is a really interesting way to distill the knowledge captured from pre-training these language models into discriminative classification supervised learning models. So there's definitely some kind of phase shift happening with how much knowledge is captured with respect to scaling up the size of these language models. This paper, Measuring Massive Multitask Language Understanding, shows this difference between the extra large GPT-3 model compared to smaller variants with respect to how they perform at these knowledge-intensive tasks. So this kind of idea of distilling generative into discriminative models is the idea behind PET. In this case, they're using these patterns that map from the generative's kind of landscape into the discriminative model space. So this idea of unifying these tasks, and all tasks are really language modeling tasks. So a similar kind of idea has been explored with generative modeling with images. It's not really similar, but it's this kind of idea of classification accuracy score. In this paper, what they do is they use the generative model to generate a data set, and then you would train a classifier on that generated data set and see how well it performs on the generated data set compared to the real data set. And this is maybe more akin to learning the distribution of the data compared to something like language modeling, where you're capturing this knowledge from this enormous data source that's really hard to reason about in the discriminative modeling task. But it's still interesting to think about this kind of transition from generative to discriminative models has a better way of evaluating the generative models. Rather than looking at how well they do the perplexity metric, how well they predict the next mass token, how well can they be used to do data augmentation or somehow supplement downstream discriminative supervised learning classification models. Thanks for watching this summary of small language models are also few-shot learners, showing that these smaller language models, the Albert model with 220 million parameters, can also perform well on this few-shot learning task where you only have, say, 32 labeled examples for some downstream supervised learning task. And this is done by using the pattern exploiting training algorithm that unifies these pre-trained language models with these downstream tasks. So hopefully this video made the PET algorithm clear and how it's implemented, how the iterative PET algorithm works, and these variants like how you design the patterns, the verbalizers, and this idea of PET with multiple masks, which seems like a really exciting direction for this algorithm. Thanks for watching, and please subscribe to Henry AI Labs for more deep learning and AI videos.